This is the second part of 20C, and we're going to look at using dot product to find the angle between two vectors. There are little tricks of the trade here, so just watch out for these. So basically we want to know, why do we use the dot product? Well, the dot product is useful for several things. One of the important uses is finding the angle between two vectors that, importantly, these vectors must have the same initial point. For instance, if I draw two vectors here, we're looking at the angle between two vectors that have the same starting point and extend outward from this angle. If A and B are our vectors, the angle between A and B, where we always measure the angle that is not the reflex angle, so the shortest angle between the two vectors A and B. So our angle will always be between 0 and pi. This is determined by the following formula. So we have that cos theta equals A dotted with B, so vector A dot product vector B, all over the length of A times the length of. Okay, here's our proof. I'm going to just draw in a graph of two vectors, and they're just arbitrary. So we can have A as vector A1i plus A2j, and it will start at the origin being a position vector and finish at the point A, which is A1, A2. I'm going to draw in again another vector. It doesn't really matter where it is, but I'm going to put it down in the fourth quadrant and let this vector be B. That's going to be B1i plus B2j. Notice they both start at the origin and extend outwards. So that is the good starting point, and thus I'm looking for that angle between these two vectors at the origin. Now I'm just going to draw in another vector from B to A, so vector BA. Let's find an expression for this vector. So I know if I start at B and end up at A, using the vectors that I already know, I would have to go backwards from B to O, so that will be negative B. And then I have to add on my vector from O to A, which is vector A. Now the reason I've created this triangle is because we know the cosine rule and we can use it to find the angle between our vectors A and B. Using the cosine rule, I know that the vector BA, or we could write this as minus B plus A. I'm going to write it as A minus B. So the length of that vector squared is equal to the length of vector A squared plus the length of vector B squared minus 2 times the length of vector A times the length of vector B times cos theta. So it's important to remember that in this cosine rule, you're looking at the lengths of each vector. Okay, let's rearrange a little bit. I'm going to take the length of A squared and the length of B squared to the left-hand side, and we end up with this. Now, there's some little things that we can put into this equation. So recall that A dotted with A is actually equal to the length of A squared. B dotted with B is equal to the length of B squared. That means that vector A minus B dotted with vector A minus B must be equal to the length of the vector A minus B or squared. We're going to sub these dot products into our star equation here. So where we see the length of A minus B squared, we're going to put A minus B dotted with A minus B. Then we have minus A dotted with A for the length of A squared, minus B dotted with B for the length of B squared. And the right-hand side, I'm just going to keep that all the same. We can expand A minus B dotted with A minus B, just like using FOIL. So we'll end up with A dot A minus 2A dot B plus B dot B, because 2 minuses equal a plus. And then I still have the minus A dot A minus B dot B. Right-hand side, again, stays the same. Notice that we have the A dot A's will cancel and the B dot B's will also cancel, which means, voila, the left-hand side minus 2a dotted with b equals to minus 2 length of a length of b cos theta. We can cancel out the minus 2's from both sides, and we have a wonderful equation here. Cos theta indeed equals the dot product of a and b over the length of a times the length of b. And we have proven this handy formula. An important note, the dot product can tell us if the angle between two vectors is acute, right, or obtuse. Have a think about how it might be able to do this. Recall that whenever we're looking at the angle between two vectors, this angle is always between 0 and pi. So let's start by drawing out a graph of y equals cos theta. Now, if cos theta equals a dot b over the length of a times the length of b, notice that this denominator is always going to be positive. A dotted with b can sometimes be positive, it can sometimes be negative, it can even sometimes be 0. Let's look at what happens if a dotted with b is positive. That means cos theta equals a dot with b over the length of a times the length of b will also be positive. Now we know that for angles between 0 and pi, cos is only positive between 0 and less than 90 degrees, or between 0 and less than pi radians. Therefore, we can say if a dotted with b is positive, we know that the angle between both vectors will be an acute angle. If a dotted with b equals 0, okay, we know the numerator will be 0 for cos theta, and the denominator would be positive. So we'll get cos theta actually equals 0. It doesn't matter what's on the denominator. Okay, if cos theta is 0 and theta is between 0 and pi, there is only one solution for cos theta equals 0, and that is that theta is equal to pi on 2 or 90 degrees. So if you get the dot product of two vectors being 0, you know automatically that the angle they will make with each other is a right angle. Lastly, I think you know what's going to happen here. If we have the dot product of two vectors and this dot product is negative, we know that cos theta, well, that will be a negative over a positive because our denominator is always positive. So we know that cos theta will be some kind of negative number between 0 and minus 1. If cos theta is negative and theta again is between 0 and pi, this must mean that our angle theta, okay, must be an obtuse angle. It must be greater than 90 degrees and less than or equal to 180 degrees by looking at the cos graph. So this means if a dot b is negative or less than 0, the angle between your two vectors will be obtuse. That's the theory behind this dot product and why we use it. Now, let's have a look at some examples. We're going to do example 3 today. I wanted to go through example 3 with you because it is a little different. First, wherever you can, always sketch these in 2D to get a rough idea and a rough estimate of your angle size or of the situation. So, we have point A, B, and C, and these are defined by the position vectors, so vectors that start from the origin. Vector A is I plus 3j. Vector B is 2i plus j. Lastly, we have a third vector C, starts the origin, ends up at capital C, and that looks like I minus 2j. It'll end up at the point 1 minus 2. We need to find the size of vector ABC. So I'm looking at the angle right here where the vector B finishes. Okay, the first thing we have to make sure always is that we need the vectors at this point to be directed outward from the point, and so that they're starting both at that point B and their direction is outward. So the two vectors that we're actually trying to find the angle between are vector B to A and vector B to C. Let's put that information in our diagram. If you have, say, an arrow pointing inwards and an arrow pointing outwards, you can't use this dot product on that angle. You have to fix it so both vectors are pointing outwards first. Before we plug in the formula, let's just figure out exactly what vector BA is and exactly what vector BC is. So remember, vector BA, I'm starting at the point B, which is 2, 1, and I'm ending up at the point A, which is 1, 3. So you can think of this either as going minus B plus vector A, or you can just think of this as how many places left or right do I need to go from B to get to A, and how many places up or down do I have to go to get from point B to point A. And we'll get minus B plus A, or vector B to A is minus 1I plus 2j. BC's similar process. You can start at point B, use vector B to get back to the origin, and then add on vector C. This could be minus B plus vector C. Again, you could just think of starting at the point capital B and how far across and how far down do you have to go to get to the point C. Both ways and both methods are valid. Either way, you should get that vector BC is minus I minus 3j. Now let's put in our formula. We have that cos theta equals vector BA dotted with vector BC all over the length of BA times the length of BC. So we need to find the dot product, the length of BA, and the length of BC. Let's do that now. Minus 1I plus 2j dotted with minus I minus 3j. Well, that will just give you 5, I think. Notice here that this suggests that our angle between the two vectors is obtuse. And if we look at the diagram, I would probably agree that our angle will be obtuse. Now we know that the length of BA, well, we can calculate that. That will be minus 1 squared plus 2 squared, take the square root, that'll be root 5. The same with the length of BC. But for BC, we'll get square root 10 for the length. Plug everything you just found into your equation. We'll get cos theta equals minus 5 over the square root of, well, root 5 times root 10 is root 50. Now, before you jump into your calculator and take the inverse here, check if you can do this by hand. We have that cos theta equals, if I break root 50 down, I get minus 5 over 5 root 2. When you cancel out here, you'll get cos theta equals minus 1 over root 2. Now, we know that theta is between 0 and pi radians, and I think the angle is obtuse by the dot product, so that means theta will be in our quadrant 2. Okay, so I can draw my identity triangle in. If cos theta is minus 1 over root 2, I can draw the triangle, and we should get a fair idea that we know this triangle has an angle of pi on 4. Remember, because theta is obtuse, I'm looking at theta from the positive x-axis all the way around. So I'll get that theta would be 3 pi on 4, which makes sense in relation to the question. Notice you can take the inverse of cos theta because theta is always going to be between 0 and 180 degrees. All right, there we have it. Here's some helpful hints to summarize this section of the topic.